Well, so we have the third. The title escapes me this time. Homological Stability of modular spaces. And we have Soren Galatius from Stanford University.
It's my last lecture. I'd like to say it's been a wonderful conference. I'd like to take the moment to thank the organizers, who are, I believe, Alejandro Adem and Isidoro Gedler, and last but not least, Miguel Higutencatl. So, thank you for a wonderful conference. Secondly, this is more to Sam. My own research has not sort of touched so intimately yet on Sam's work, but I'm learning about it right now. At Harvard University, they have so I'm on sabbatical at MIT for the moment. So they have a Thursday seminar where each semester they decide on some topic that they think this is important to learn. It's run by Mike Hopkins and Jacob Lurie. And this semester they've decided to learn about Brown-Gittler spectra. I don't know if you know that, but every Thursday there's a learning seminar on Brown-Gittler spectra at Harvard now. So I hope to learn more about your work. So today's lecture I sort of mentioned what I was going to talk about. So the title was Homological Stability. Or moduli spaces or something. Let me briefly recall a few definitions from the last lecture. So the statement is going to be something like a certain map induces an isomorphism in homology from degree 0 up to degree something. But let me recall what the spaces are that we're talking about. So first of all, we fix, well, a number. Most of the time it will be strictly bigger than 2, but the definitions make sense, bigger than or equal to 0. And we fix a map called theta. It should be, I don't know if I said that, it should be a Serre vibration, for technical reasons. And then it should be n co-connected. And that means injective in pi n. And isomorphism in bigger degrees. Say it that way if X is connected at least. So that's the input, and then there was a bunch of definitions associated to this. There was one more input, then there was a 2n minus 1 dimensional closed submanifold. Okay. So this is going to be, 2n minus 1. This is going to be the boundary of all the manifolds in a moduli space of manifolds. That's called n theta of p. So it's the, as a set, it's the set of submanifolds, minus infinity, comma 0, or R infinity. With the property that the boundary is equal to P. So 0 cross P. And equal means equal should be the same subset. So there are a few more data. Then there should be bigger picture. So the picture you can draw is here's a circle or something. Then is 1. P could be maybe 2 circles embedded in some way. And W would be a null bordism of that. So something like this. And 0 minus infinity is this direction, and everything else is R infinity. So that's the condition on the manifold. So it should be 2n dimensional and compact. And then there should be some bundle data as well. So that should be a map L from W to X with the property that it's a lift of the tangent bundle. So if by BO2n I always mean the Grassmannian. So since my manifolds are submanifolds of R infinity, they come with a preferred classifying map for the tangent bundle. And I want, I take L and I compose with theta. It should be equal to the classifying map for the tangent bundle. Write that as TW. So L is a lift of any W has a canonical map to classifying the tangent bundle to Grassmann 2n of R infinity. And as part of the data, I specify a lift. That's part of what an element in the space is. And then the lift should agree with an already specified lift of the tangent bundle on the boundary. Yes, yep. So that's an orientation of a surface would be the interesting case. So that should also, as part of the input, I take the tangent bundle of P, stabilize it once, we get a 2n dimensional bundle, and there should be a specified lift. Let me decorate that with an LP. And I'll, one thing at a time. Yes, I'll write that once I've finished saying this. So one condition is that boundary of W should be P. Another condition is that L should be a lift of the tangent bundle. And the third condition is that the lift of the tangent bundle of W should agree with the already specified lift on the boundary. So L, W, respect to the boundary W. LP. So that's 3 conditions on this pair of a manifold together with a lift. And the fourth condition, as Rustam asked about, is that L should be n-connected. Where n is the fixed n, so it's half the dimension of W. I'm not sure I understood that. So I wrote what n co-connected means here, and maybe I'll write what n connected means. means that it's surjective in pi n and isomorphism in degrees less than n. So this factorization of W to X to BO to n, the map induced in pi n is the factorization of the original homomorphism into the image and the inclusion of the image. And then above and below that, the homotypic groups of X are either those of W or that of BO to n. So this is a lot of data, but it's sort of good to think of some examples. So if n is 1, theta could be BSO2, BO2. If I convert that to a vibration, could for example take the universal cover of BO2. Then the LP, LW, specifying a lift of the tangent bundle amounts to specifying an orientation. So in that case, specifying this map is an orientation of the boundary, and then you look at all possible null vortices as oriented to manifolds. And then the condition that L is 1 connected. So that means surjective in pi 1 and injective in pi 0. If W is a 2 manifold, so an element in n theta of a circle or 2 circles will be a pair of a W, an LW, and the condition on LW is that it should be 1 connected. And that just says that W is not connected. So this should be injective in pi 0. Another example is if this is the identity map of BO2. That's a new example. Then this condition where specifying a lift is no data, but I mean there's a but the condition that that map is 1 connected, so it should be an isomorphism in pi 0, so W should be connected, and then it should be surjective in pi 1. That's saying that the surface should be non-orientable. Not connected. So it's non-orientable. So in both those cases, there's sort of better descriptions of what this moduli space is. I want to describe the homotopy type of it. So when theta was BSO2, BO2, and theta of P. It'll be a classifying space for oriented surface bundles with a fixed fiber-wise boundary being P. So and there should be bundles of oriented connected surfaces. So the homotopy type of this will be disjoint union over genus and B of the classifying space of genus D surface. The boundary components if P is the disjoint union of B copies of the circle. that's a translation of what all that data means. And similarly, in the case where theta is the identity map, it should be well, similarly, but with non-orientable connected surfaces. So last time I talked about how to, in some sense, describe the some kind of limit of the homology of this kind of space. And limit involved gluing bordisms. Okay. Gives so from P to Q. So that means the boundary is 0 cross P union 1 cross Q. Gives this map. If you have a null bordism of P, you get a null bordism of Q. By gluing on the bordism, well, you also need to specify the bundle map. So I should also specify a lift of the tangent bundle of K. So given a pair of a bordism and a lift of its tangent bundle, there's an induced map of these moduli spaces. Induced by gluing the bordism and gluing the bundle maps. So in the picture, well, you could glue any bordism from any number of circles to any other number of circles. There's one condition, namely that the pair K comma P should be n minus 1 connected. That ensures that if this map is n connected, then this one is as well. So in my last lecture, I talked about what is kind of the limit of the homology of these spaces in a limit where you glue more and more bordisms. And in this lecture, I want to talk about homological stability, that each of these maps induce isomorphisms on certain parts of the homology. So this map. Provided n is bigger than 2 and x is simply connected. And parts of the homology means from degree 0 up to degree something, and the something depends on what part of the component you're in. So let me try to state that a little more precisely. So there's an invariant of higher dimensional manifolds that correspond to genus. So let me define that. So if let me write WG 2n for the connected sum of G copies of Sn crosses n. And if I have some arbitrary 2n dimensional manifold, I'll say the genus of that manifold is the maximal number of maximal G, so that W is diffeomorphic to the connected sum of this manifold and some other manifold. for this to be well defined, I should require W to be connected. So for oriented surfaces, that agrees with the usual definition of genus, and this is a natural generalization. I also want, this doesn't quite behave always the way you think it does. Like if you connect some W with Sn causes n, it's not clear that genus goes up by 1. But you can fix that by taking the maximum of G of W connect sum Wk minus K by K bigger and bigger. I'll call that the stable genus. And this behaves a little bit better than the ordinary genus. So this has the property that if you connect some within Sn crosses n, the genus goes up by always by 1. So the different components of this space of null Bordisms with tangent, with left of a tangent bundle, they're different path components, but to each of them there's a number associated, namely the stable genus of the underlying manifold. The stability range will depend on that. So let me write the space of all null Bordisms will be the disjoint union over G bigger than or equal to 0. Where this is the subspace consisting of pairs of a W, LW, where the stable genus of W is equal to G. So in the oriented surface case, it will just pick out precisely one path component, namely the genus G surface. So then I'm almost ready to state the theorem. So if you glue on any Bordism can be written as diffeomorphic to the composition of a finite collection of elementary Bordisms. So if K is elementary Bordism, so that just means it admits a Morse function with precisely one critical point. So, or in other words, a Bordism from P to something else. So you start with the trivial Bordism, and then you attach a handle, and those handles have some dimension. So let's say it's a K handle. And you attach it along an embedding of the boundary of the handle, boundary dk equals d to n minus k, into the into 0, 1 plus into 1. So, for example, P is a circle, an elementary Bordism of index 1. You cross the circle with an interval, and then attach a thickened one disk. Then you just through the corners, and you get a Bordism that's diffeomorphic to a pair of pairs. Yep. I'm not sure if I said that. I said last time that, well, so without the else, then the components of the moduli space's embeddings of a manifold into Rn modulo diff. But now I've taken, well, n was something different last time. Now I'm talking about submanifolds of R infinity. So the embedding space is contractible, so if you mod out by diff, you get a model for B diff. In this example I was discussing here, specifying a lifting just amounts to specifying an orientation, and that's why you get B of the orientation preserving diffeomorphism. It's meant to be easy enough to follow. Yes, so there are some special cases. Well, I mean, this is always true if you write it this way. If there's no boundary and the genus is 0, then this is not a k-pi1, but this is still what it is. Embeddings for that component will be embeddings of S2 cross the space of orientations of S2 divided out by the diffeomorphisms of S2, and that gives you B of the orientation preserving diffeomorphism group of S2 because the space of embeddings is contractible. Embeddings modulo diffeomorphisms is B diff. Yeah, so in general, this construction of this in general would be the Borel construction of the diffeomorphism group acting on the space of tangent bundle lifts. So if you want to prove that gluing a Bordism, the boundary manifold induces an isomorphism in homology of the moduli spaces, you might as well just consider elementary Bordisms, because if you can prove it for those, then any other Bordism will be the composition of elementary ones. And for this pair to be n minus 1 connected, this k should be between n and 2n. So I want to prove that gluing on an elementary Bordism induces an isomorphism in homology of the moduli spaces in a range that depends on the genus. So now I can at least state the precise version of the theorem. I should say all of this is joined with Oscar Randall Williams. So if k is strictly bigger than half the dimension, you're gluing on a handle of dimension strictly bigger than half the dimension, and it's easy to see that it doesn't change how many connected subhands of Sn cross Sn you have. So you get a map from n theta G of P. Gluing on this elementary Bordism. Okay. So Q is just the outgoing boundary. What it is surgery on P along this surgery data. But it's just the outgoing boundary. And if k is equal to n, gluing an n handle might change the genus. I'm not done yet. I haven't written the conclusion. that's going to be the same conclusion about these two maps. I wanted to write them both. But the statement is going to be that this is an isomorphism in homology up to degree g minus 4 over 2, under the assumption that x is simply connected and n is bigger than 2. But it's going to be the same as some conclusion here. Except gluing on an n handle changes, or might change how many connect some n's over n causes n you have. In some slightly uncontrollable way. But if you glue both the Bordism, K is a Bordism from P to Q, I can reverse the Bordism and get one from Q to P. If I glue those together, let me call that K bar. K was P to Q. And K bar is just a mirror image with the reversed bundle map. So gluing both of them will always increase the stable genus by precisely 1. So the statement of the theorem then is that provided you're not in dimension 4, provided all your manifolds are simply connected, then both of those two maps induce isomorphism and homology in the range. As long as star is not bigger than g minus 4. Oh, and I forgot the assumption. N is bigger than 2. And I want x. And x is simply negative. So that's the homological stability theorem. And my scanning method I talked about last time will then, in some sense, calculate what the homology is in that range. Yes. How much time do I have, by the way? Yes, sort of. Yes. Minutes left. Minutes left. Yeah. Ah, okay. So yes, yes, these are sort of BDEF. These spaces map to BDEF, and the fiber is this space of liftings of the bundle map. Right. So let me just, before I say something about. So we've not used n co-connected a lot. This would definitely be false if I don't impose the condition that the lift is n connected. Like there's a bigger space where you remove that condition. So in theta, it consists of pairs of a W and a lift, and the condition was the lift should be n connected. If you don't impose that, then even for surfaces it goes wrong. You would have path components. So if you have non-orientable surfaces, you might still have some path components that correspond to orientable ones. And if you glue something non-orientable on it, would be like to prove a homological stability for the inclusion of an orientable surface into a non-orientable one. Well, it's in the definition of n theta. It's in the definition of n theta. Maybe I should write the definition again. Maybe I could try to leave it here. N theta of P. It was pairs of a W inside minus infinity 0 outside infinity. And an LW That's a map from W to X with the property that it lifts the tangent bundle. And then there's a bunch of conditions on these two. So specifying elements means specifying these two things, but then there was a million conditions. An important one was that this map is n-connected. And then like the boundary should be something specific. With the fiber, well, if you forget the LW, then you just have the embedding space module of the diffeomorphism group. So that's a model for B diff, well bounded. And what you're forgetting is the space of bundle lifts. So yeah, it's a classifying space for, B diff classifies smooth fiber bundles, and this classifies smooth fiber bundles together with a lift of the fiber-wise tangent bundle, sort of a bundle, an extra structure on the fiber-wise tangent bundle. Yep. P. Well, P does not need to be highly connected. No, so P is the boundary of W, and it's sort of right from W to X, and it's not. There's no conditions on what P looks like relative to W. Yep. Yep. So Bill complained that there hadn't been very many infinite loop spaces, so let me write one. So I didn't write the conclusion this way in the last lecture, but let me do it now. In this range, hi of n theta g of p agrees hi of the infinite loop space corresponding to a Thom spectrum over X. And it should be the Thom spectrum of minus the vector bundle classified by theta. I'll write that as X to the superscript minus theta. So theta is self-classified an actual vector bundle, and minus that is a virtual bundle, so you can take Thom spectrum of that. So this is, I mean, in many cases you can at least figure out what the rational cohomology of this is. Although I didn't quite say it that way. That's the output of that scanning stuff. Yes. That's your second idea. Yep, yep. Right. And that somehow separating those two things seem easier than trying to work at finite genus. And the proofs are completely separate. There's one method for proving stability, and there's another one for determining what is it in the limit. And sort of, like this theorem has this assumption, but without those assumptions, we can still figure out what the limit is. We just don't know whether it stabilizes. So they're quite orthogonal steps. I should perhaps say well, it might take infinitely far. It might, for all we know, it might be, like we calculate what the direct limit is, but it might be sort of a non-stabilizing direct limit. And also in the non-simply connected case, for all we know, it might, we're just calculating the direct limit. I should mention one important precursor, and that's Harrah's theorem. Which is essentially the case, essentially equivalent to the version of this statement where theta is BSO2. In that case, where I wrote an interpretation of what in theta P means, and under that translation, this corresponds to Harrah's stability theorem for the classifying space of matter class groups. But so that case was known from the 80s. Yes. Let's see. So how do we? Okay. Unless there are more questions, I want to say some words about how we prove that. So it's important to prove this in the right order. It's sort of going to be an induction on K, where we start with K equals N, and then we work our way up to K equals 2N. So there are several steps. First, there's a special case of K equals N. So in the case K equals N, I want to glue both a handle and its kind of dual handle at the same time, mainly because I want to control the genus. So that can look, there's sort of various ways that can look like. So I just start, N is 1. Start with a circle. First you glue a one handle. That might look like this. And then you glue a dual one handle. That will look a lot like, what did dot go? It looks like your prop, almost. This is maybe not so easy to see what this looks like, but it's a pair of pants. That's the first one handle. And then I just do that in the opposite order. This is K, this is K bar. So you can see if I happen to start with this particular one handle, then gluing K and K bar is the same as connect summing with S1 plus S1. And that's actually not an accident. That's because the one handle is attached trivially. So this is a trivial handle. That just means that the gluing map sort of, it all happens inside a disk and P in a standard way. That's the beginning of the induction, proving that case. So trivial one handles, gluing K and K bar, up to diffeomorphism is the same as gluing a cylinder. Connect sum is N plus N. So we first prove that. So that's step 1. So that was, we call that TP. T for torus. It's kind of a generalized torus. With some quantum structure. So step 1. Prove that in this case, homology in this range. That's, in any case, a special case of what we're claiming to do. But then, once you've done that, you sort of don't have to worry. You can get around. So there's a certain commutativity that happens. Commutativity of Bordisms that you have any other handle of index between n and 2n minus 1. So it starts at p and it ends somewhere. Maybe it looks like this. Ends at q. Q is not going to be empty when k is not equal to 2n. If you glue on a torus on the right-hand side, it's diffeomorphic to gluing a torus on the left-hand side. You can sort of pick a path and slide it along the path. So, GQ looks like this. It would be Q across an interval connects on this n crosses n. Ordered from Q to Q. It's diffeomorphic to sliding this one over to this end. And then I have TP composed with K. Well, that's probably clear enough in this picture, but it's also sort of easy to prove. The proof is essentially sliding this n crosses n down to this end. So suppose I've already proved step 1, then the fact that these two are diffeomorphic means that the map, the two gluing maps, so if I start at n, these at p, I glue TP. So this is just connect summing near the boundary with this n crosses n. If I then glue K here, and these at Q, so I first glue TP and then I glue K. That's the same as first. Oh, this diagram is kind of confused. These manifolds being diffeomorphic implies that this diagram is homotopically confused. Well, if I'm trying to prove this induces an isomorphism in a range. I already know this induces an isomorphism in a range. I can keep taking the direct limit over going further and further out. And that gives me a commutative diagram from this particular, well, take homology. Then I get a commutative diagram. So this maps to the direct limit of the homologies, so does this. The diagram commutes. So if I could prove that K induces an isomorphism in homology in the limit, of the direct limit, and these maps are isomorphisms in a range, then it implies that this is an isomorphism also at a finite state. So let me summarize this. So K induces some homology of theta T. Homology of Q. The fact that this diagram homotopically commutes means that it commutes in homology, and another way of saying that, well, we can think of this as a Z adjoint T module. Because gluing on this torus gives a self-map of the space, and that makes the homology into a module over Z adjoint T. And this diagram says that this map is Z adjoint T linear. And it now, once we've proved step 1, it suffices to prove that this map induces an isomorphism after inverting T. Step 2. Iso after centering over ZT. Forming that localized set an isomorphism, and you know the maps in the direct system are isomorphisms in a range. It follows that the maps at the finite states are isomorphisms in that range. And then there's a final step 3 that I want to talk about, which deals with the remaining case, where k is equal to 2n. But there's essentially, it's only step 1 you need to keep track of the genus. Once you've done that, you can sort of work an infinite genus from then on. Yes. How much time do I have now? 10 minutes. So step 3 is not kind of not very difficult. Step 2. Step 1 and step 2 are very different. Maybe I can say a bit about how we prove step 2. Step 2 is a bit more formal than step 1. We want to prove that gluing a handle of index k is from n to 2n, induces an isomorphism in homology after gluing after connect summing infinitely many times with Sn crosses n. So there's one case of that's easy. Because we already infinitely many times glued Sn crosses n. So if well, I can sort of compose this with I write k bar here as well. It also commutes. So in the case where this map is also just connect summing with Sn crosses n, that's sort of what I inverted. So then it's just formal properties of direct limit that says that induces isomorphism. So there's a baby case. So if k is equal to n, and k from p to q is elementary Bordism, corresponding to a trivially attached n handle. I already said this once. Then k bar k was diffeomorphic to what I call TP. So of course it induces isomorphism of homology of n vis-a-vis p to itself. After inverting T, because I precisely inverted the map that I want to be an isomorphism. Yeah, sure. I think I can write the formal definition, or I can draw some pictures. So the input was an embedding of boundary dn cross dn into p, and the output of that is so k is then defined as 0, 1 cross p union with dn cross dn over this embedding of the boundary into trivially attached means if you rewrite this, see, so boundary dn cross dn. If I write this as boundary dn cross d1 cross dn minus 1, I can think of this d1 as a kind of radial coordinate. So this is a sphere cross an interval. I can think of that as an annulus. So this is an annulus inside dn. So this whole, if you rewrite it this way, it naturally sits inside dn cross dn minus 1. And trivially attached just means that this embedding is the restriction of some embedding of that space. Like this, so I think it's called trivially attached, and I think a picture is better. If you start with a circle, the picture I drew before is trivially attached. So here's a picture of S0 cross D1. Actually, whether it's trivially attached depends on what way, how you orient the D1. The one I drew is trivially attached, but if you do it the opposite way, you end up with something like this, which is not trivially attached. There's no way to extend this to the embedding of the diagram has to commute. And you can also, this in fact will be RP2 minus 2 disks. But if it is trivially attached, and you take the corresponding bordism and its mirror image, that will always be diffeomorphic to just a cylinder connect some and then cross it. So if I happen to want to prove stability for a trivially attached n-handle together with its dual, after inverting T, there's nothing to prove because I precisely inverted the thing that I'm trying to prove is invertible. So that's easy. So that's the beginning of the induction. Then the next step is n-handles. So still in the middle dimension, but those that are not trivially attached. Last thing I say. 3 minutes, okay. I'll just say what the idea is. Non-trivially attached. So for example, that case was not trivial because of the orientation issue, but there's sort of an even more trivial case where you do this one handle. There's no orientation problems, but there's of course no way to extend this to an embedding of a disk. So I'm supposed to fill this in with a 2 manifold here. So the idea there is that the idea is to cut out another k-handle, so k is equal to n from W with sort of parallel boundary conditions. What does that mean? So in this case, the boundary conditions, I mean the attaching map for the one handle. If you perturb it a little bit in one of the normal directions. Suppose you could embed a one handle in the manifold. No, I mean you can't do that in families, of course, but suppose you could happen to be able to. If you cut that out, then suddenly the one handle looks trivial. W. So then so after cutting that out, the N handle is trivially attached. To the complement, it's trivially attached to the manifold you get after cutting it out. So then you have homological stability for attaching this N handle together with this dual cell. And well, I'm out of time, but the idea then is to say we have this space that's roughly B diff. And we're going to make a simplicial space over it where the zero simplices include a choice of such an N handle in the manifold. And the one simplices are disjoint pairs and such things, etc. And maybe you'll allow me 2 more minutes. Yes, it's very much like like the arc complex. I mean, in fact, it is the arc complex in the case I drew. Except we only ever care about it in infinite genus limit. So define a simplicial space. X dot. It's augmented. So it sets over in these are P. And the space of P simplices is pairs of an element here together with a P plus 1 tuple of it's a W, LW, P plus P plus 1 tuple of disjoint. Handles. So that's dn cross dn inside W with some specified boundary condition. So I have E0 of 3P of those. And the idea now is that the gluing map, K bar K, is covered by a map of simplicial spaces. But now in each simplicial degree, the map will look like you're gluing a trivial N handle and its dual. And therefore, by the first case, it will be an isomorphism after inverting T. And then what remains to prove is that this is kind of a resolution, that the realization of this simplicial space is weakly equivalent to a P. And that's how we prove the general case of an N handle and its dual.
Any questions?
So the beginning, so I didn't talk about that at all. Well, it depends on what you want to prove. So the beginning of the induction was attaching a trivial N handle and its dual. That's an isomorphism in homology after inverting T. That sort of follows by formal properties of direct limit. There was a step before that had some assumptions, where I proved that gluing, what I call T, induces an isomorphism in a range that depends on the stable genus. So either of those can be regarded as the beginning of the induction.
Ralph?
So in Herer's original argument in the n equals 2 case, and then those that came after that improved, one of the hard parts was always showing the arc complex was highly connected.
Yep.
So is is there an analogous issue here? Is that the statement about being a resolution or something?
So that's in the part. There is an analogous statement, but it's not nearly as difficult here, because this is sort of like proving the. I only want to prove this in the limit where g goes to infinity. And it's fairly easy, even in the surface case, to prove that the arc complex is contractible if you're allowed to glue an infinitely many tori on. So that's all. That's sort of also, I mean, in retrospect at least, not so difficult. There is a step that's closer. That's when the one step where we keep track of genus. That if you go from genus or stable genus G to G plus 1 by gluing on interval cross P connects some as n crosses n, that induces an isomorphism in some specific range up to G minus 4 over 2. There we have to prove that a simplicial space whose zero simplices are essentially embeddings of as n crosses n minus a disk. And P simplices are P plus 1 tuples of disjoint embeddings. We have to prove that a simplicial space like that is highly connected. Depends on your point of view, but that's my point of view. Is there one place where there's a definite range? Everything else just carries the range along. And is there one place where you can't first take the limit and then prove isomorphism in all degrees in the limit? So you have to be a lot more careful and keep a lot more track of what's going on in that case.
So this space n theta p, it consists of many components, right?
Yep.
And so the theorem is actually about these components. So
it's actually also about H0.
Right. So this was actually my question. Can you explain kind of, is there a geometric idea? How can you see that after stabilization, different components, they homologically become the same? So basically you start with different manifolds, then after you attach handles, it just becomes the same. So why, how do you get this phenomenon?
So maybe I should have said that the H0 case, like this homological stability for H0, if you write out what that actually means, it reduces to some theorems that were already known, like cancellation theorems. For example, if you know, here's I think most of those are due to cracks maybe. So if you know that M connect sum is n crosses n, is diffeomorphic to M prime, connect sum is n crosses n. Can you deduce that M is diffeomorphic to M prime? And you can't always. But it is. So stability on H0 says that the different components, like you might have different components that somehow become the same after stabilizing once, but that does not keep happening as genus gets bigger. So at some point you have a cancellation theorem that if you're in the same component here, then you're already in the same component there. And if you spell out what that means in H0, it's precisely a cancellation theorem like this. For something like this, except you also have a boundary and you have this.
Well, let's thank our speaker. Two announcements. The first is that after all this ends, the speakers or gave a talk and whatnot should walk to the library of the Colegio Nacional to pick up the collected works of Sam Gittler. If you don't want to carry them, they will be mailed, but if you want to carry them, you can pick them on immediately after this. And just to end it all, I would like to have a standing ovation for Sam for his 80th birthday.
On the contrary, I want all of you thank you for coming with us and being with us.